Let's move to the second problem, and the second problem is displayed on the screen. The problem reads: a radioactive nuclide with half-life capital T is produced in a reactor at a constant rate P nuclei per second, and during each decay energy E0 is released. If the production of a radionuclide is started at T is equal to 0, we have to calculate first the rate of release of energy as a function of time, and the second part, total energy released up to time T. Now again we have to move into the solution of this problem. Let us assimilate what is given and what is to be calculated. In the question we have a mention of radioactive nuclei being produced in a nuclear reactor at a constant rate. Also we are given the amount of energy released in each disintegration, and there are two parts of the problem. In first we have to calculate energy released as a function of time, and in second part we have to calculate the total energy release up to time T. Now let's move for the calculation. First let's have a relevant differential equation. Let us suppose at any instant of time the number of nuclei in the radionuclide be a capital N, then we know that rate of decay will be simply lambda n. That is the radioactive law, that is the rate of decay at an instant is proportional to number of radioactive nuclei left. Now at any instant, net rate of accumulation of nuclei dn by dt, here dn by dt represents rate of accumulation of nuclei. Now we are given in the problem that radioactive nuclei are being produced at a constant rate P. So our relevant differential equation will be dn by dt is equal to P minus lambda n. Now when we just make a rearrangement, we can rearrange this differential equation and we can write dn over P minus lambda n is equal to dt. Now we can write and integrate this differential equation both sides, where our limit will be for dn, the variable will be from 0 to n, and for time it will be 0 to t. Now we know that the value of lambda, now lambda is representing the disintegration constant, and in terms of half-life it is log 2 divided by capital T, which is the half-life. So making this substitution, we have final expression integration limits from 0 to n dn pt in denominator minus n ln t is equal to 0 to small t, integration limit on the right hand side, dt divided by capital T. Now when we solve this equation, we get the final solution, that is number of nuclei at any instant of time, and the expression is shown on the screen, and it is n is equal to pt divided by ln t in bracket 1 minus e to the power t ln 2 divided by capital T. Similarly we can write the activity. Now this activity will be simply A is equal to lambda n, and activity as a function of time is shown on the screen. Now it is given that energy which is released in each disintegration is E0. So the rate of release of energy at any time t will be simply the activity of the radioactive nuclei, that is A into E naught. So we get the answer for the first part, that is the rate of release of energy at any time, that is function of time. Now just to make calculation for the second part, where we have to calculate the total energy release up to time t. Now we need to calculate the total number of nuclei which have decayed up to this time t. So nuclei decayed up to time t will be simply P into T minus N. P is the constant production rate and N is the number of nuclei left at any instant of time. So again making substitution, so energy release up to this time will be obtained simply by multiplying the number of nuclei decayed by E naught. So energy release up to this time t will be Pt minus N in bracket multiplied by E naught. Now making substitution for N, which we have done earlier, that is number of nuclei left as a function of time, we get the expression for energy release up to time t. Now this was again a simple problem involving the definition of activity and the decay equation for radioactivity. And the most important part which goes in every problem, understanding what is given and what is to be calculated.